Hi, in the previous lessons, you saw how to find shear forces and bending moments in particular locations. Now our task is to actually go the next step and find shear force diagrams and bending moment diagrams. This is what we mean is shear force as a function of x and bending moment as a function of s. In order to do this efficiently, we have two major results that help us figure out how to do this. The first result says that dm dx equal to v. This is the math speak for the following idea. Slope of the bending moment is the shear force. So in other words, the shear force, the bending moment will always be 1 degree polynomial higher than the shear force because it's the integral, right? And the other thing is, if you know the shear force diagram, you already know the slopes and you can kind of sketch the bending moment diagram fairly easily. So if your shear force diagram is a triangle, your bending moment diagram will be a parabola and so on. Okay, the second thing is, the slope of the shear force diagram is the distributed load. So if I know this, so this is the same kind of thing, slope of shear force equal to distributed load. And if you combine 1 and 2, you will get d squared m dx squared equal to q. So curvature of Bmd equals distributed load. Also, jumps in shear force equals concentrated load. Jumps in bending moment equals concentrated moment. Here upwards positive, here clockwise positive. So what I mean is, if I have a concentrated moment which is clockwise, then there will be a corresponding jump in the bending moment diagram which is up. Okay, so we will see these examples. So once we have these rules, so I want you to remember, don't memorize the equations, memorize the words. I really want you to memorize these things because this will help you very much. So slope of the bending moment is the shear force. Slope of the shear force is the distributed load. Jump in the shear force equals concentrated load. Jump in the bending moment equals concentrated moments. Clockwise positive. Okay, so let's see how this works. So I want to find the shear force and bending moment diagram for this. In order to do this, you need two things. Get your trusty calculator out, get a ruler out, because we are going to be able to draw this in a fairly careful way, and it's better to do it in engineering paper so that it's easy for you to draw the pictures to scale. Okay, so first step is mark the axis y x. So that's step number 1. Step number 2, find reaction forces. In our case, we already did that, and draw a large FPD. Now what I want to do is redraw this beam almost to the entire length of this thing. So I want to redraw this beam as if it's a long beam that goes all the way, and I'm going to try and see if I can make it from here all the way there. Okay, now why do you draw it long? Because then it will be easy for you to see specific points. Okay, then draw all the forces So that force was 8 kips. And then there was a force here, 6 kip. And there's a force there, 12 kip. And there's a force here, which is 10. Okay, so that's a 6 kip force, there's a 12 kip force, there's 8 kips, and there is 10 kips there. Okay, now what we are going to do is actually use these things as guides for the shear force and bending moments. Okay, so I'm going to draw another line right below it so that we can draw the shear force diagram. Leave yourself plenty of space because the shear force diagram goes both positive and negative, so make sure you have space and draw it in this with the same length right underneath, like what I'm doing. Okay, so make sure you are drawing it right underneath. Oops. Like that. Okay, now so this is the bending moment, sorry, shear force diagram, and what the key idea is the following: jump in the direction of the load. That's the key thing to remember. So what I mean by that is I'm going to start here, and can you see that the load is 8 kip and it says pointed upwards. So I'm going to jump up by 8. 1, 2, 3, 4, 5, 6, 7, 8. There you go. So that's the starting point. Okay. Then, so and in order for this not to interfere, I'm going to kind of select it and move it somewhere else. Let's see if I can. Must be something which says select, right? I used to have it, but now I don't have it, so let me erase it. So I'm going to erase this thing. So I have jumped up by 8. So then what do I do? Notice that this jumps in the slope of the shear force is a distributed load, right? So look here, there is no distributed load, so the slope is 0. So I'm going to go horizontal all the way up to here. No distributed load, which implies slope is 0. And then here it says jump down by 6. 1, 2, 3, 4, 5, 6. So I'm going to jump down here like that, and then go all the way down here, and then jump down by 12. So that's that. That's that. So I'm going to go like that, like that, like that, and then jump down by 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I'm going to jump all the way down here, and then again 0 slope. When I come to the end, jump up by 10. If you count it, that will be 10. There's your shear force diagram. And this is kilonewtons. Okay. So that's it as far as the shear force diagram goes. We'll draw the bending moment diagram next. And you'll really need some space for this. So I'm going to move this up a little bit. And as usual, I'm going to draw a straight line along the edge so that we can use that. So let's move all the way down here. You can see I'm trying to give myself a lot of space because these things can and do take up quite a bit of space, right? So there is my line, and there are the locations. Okay, so for the bending moment, I go back to the load diagram. There it is. This is my load diagram. That tells me what the loads are. Notice that there is no concentrated load here, so the bending moment will start at 0. And the slope is now 8 units. The slope is shear force, so I know it has to go up. That slope is 8. How far does it go? With a slope of 8, it goes all the way to this point. The area under this curve, that much, will be the height to which it will go. So the area under this curve is, you can see, the area is integral, right? So we are saying bending moment is integral of the shear force. That's all we are doing. So the area under this curve is 8 times 6, so it goes up to 48. So I'm going to go roughly somewhere here, and I'm going to say that's 48. So it goes like that. And so that's 48, and and just to make sure, that's the area under the curve. Why is it a straight line? Well, for two reasons, right? I can look at this and I can say slope is constant, so it's a straight line. I can also look at here and I can say curvature is 0 because there is no distributed load, so curvature 0, so straight line. Okay. Then what happens? It's going to go further up. Can you see? With a reduced slope. The slope is now 2 instead of 8. And it will go like that. So now this slope is 2, which is this value. And this area, this height equals 2 times 6, that's 12, that's this area. So we are now reached up to 60. Now what happens? Can you see that the slope is negative? So it's going to come down. I'm going to draw this in a different color so you can see. So there's the bending moment. There's the bending moment. I told you we need more space, right? See, I almost ran out of space. So I want you to understand that if you're going to draw the bending moment diagram to scale, you will need lots of space. And then I'm going to come all the way down. I know it will hit 0. So I'll go like that. The slope will be negative 10. That's this height. So did you see how I got the bending moment diagram? So I use the slope to draw the line. I use the area to find this point. So this point is given by this area. This point is given by the sum of these two. And this point is given by the sum of this and this and this. You will see that the area here will be exactly equal to the areas there. So I'll get 0. Okay. So that's how you draw the bending moment diagram. I hope you got this idea. So what we do is you first draw the load diagram, then jump up with the concentrated load. So if it goes up by 8, you go up by 8. If it goes down by 6, you go down by 6. By 12, up 10. And then use this to draw the bending moment. This actually enforces these three conditions. dm dx equal to dv, dv dx equal to distributed load, jumps in shear force equal to concentrated load, jumps in bending moment equal to concentrated moment. Notice there is no jump in the bending moment at all because in this case there is no concentrated moment.